What I'm going to talk about today is primarily contained in this document, which was published by AASHTO in the year 2003. So it sounds like an old document, but things don't move that quickly in the bridge industry, as you all know. And many of the topics that we're going to talk about are questions that had been around for years. In the year by the time 2003 came, we continue to get those questions. Much of what I'm going to talk about for the next 40 minutes is founded in what are these people, what do you people need to know day in and day out, what kind of questions do we get, and what are the answers? And really the answers haven't changed much in the last 10 years. The full title of this document is Guidelines for Design for Constructability. So what we're going to talk about are simply guidelines, good for most bridges most of the time. And I'm going to talk primarily about girder type bridges, whether it be a roll beam or a plate girder. I'll give you some brief background on the steel bridge collaboration and where this work all came from. The steel bridge collaboration is a true public-private partnership between government and industry. Government is represented by AASHTO and the state DOTs. Industry is represented by the steel bridge fabricators, the suppliers, the contractors, and the consultants. So these folks all get together twice a year, and our mission is to develop standards that could be adopted by any one of the 50 states and hopefully by all of the 50 states, so that someday down the road there'll really just be one way to design and build a steel bridge in the U.S. rather than 50 different ways, which is what we have today. On an industry basis, we believe that will lead to much more economical situation for steel bridges, keep us competitive in the marketplace, and provide a better product for all of us to use. These guidelines started out as a survey form that went to the 50 state DOTs and about 15 major steel bridge fabricators across the country. I think it was about an 8-page survey. And the questions were basically, what do you do in this situation? What do you do in that situation? What do you prefer to do here? Why do you do it that way? What are the benefits and what are the downside of any one of these things? All that information came back to a task group that spent, I don't know how many man-hours, sort of distilling it all down and trying to come up with the best of it and find the nuggets in there that would let us build safe, economical steel bridges. That was then subjected to a voting process. It went out 3 times for votes. Anybody that voted negative, the task group had to kind of resolve that negative vote and either find it non-persuasive or actually somehow consider it in the document. Ultimately, we arrived at a consensus. Not everybody agrees with everything in here, but most people agree with most of what's in here. Functionally, the Steel Bridge Collaboration is a working group beneath the Steel Bridge Committee in AASHTO, which then goes up to the Standing Committee on Highways at AASHTO. And these documents that come out of the collaboration work their way up through the AASHTO approval process and ultimately become AASHTO documents. The document I showed the title of on the front slide is available from the AASHTO website. If you find your way in there, you can go to the AASHTO bookstore and you can actually download this document for free. It's also available on the NSBA website, where it's much easier to get to. I'll show you that at the end. But anyway, that's where it came from. In a nutshell, these are the 6 sections or chapters that are in the book. And I'm going to go through each one of them briefly. We don't have sufficient time to get into everything that's in here. So I've tried to just pick what I think is appropriate for shorter span steel bridges. Getting into the design section, this first design section has to do more with the general overall design of the bridge, how it's laid out, and how it's going to be put together eventually. These are the questions, again, that we get day in and day out. We'll look at each one of these issues specifically. I don't know how many times I've been asked the question, what should I use, a roll beam or a plate girder? I've got a bridge that's 110-foot span or whatever. And the simple answer is, if the roll beam will do the job, then that's what you should want to use. That's going to be the most economical solution. With the roll beams that Nucor makes available now up to 44 inches deep, you can probably run a roll beam to maybe 100, 110, 120-foot span, pushing a little bit, but you can probably make that work. And if you can do it, it's going to be the most economical. There are a couple of things to consider if you're trying to decide a roll beam or a plate girder. One is availability of the material. Oddly enough, roll beams are available sort of in the marketplace, not necessarily to the same extent that plate girder, that plate material is. Roll beams supply to a whole different market, aside from just bridges, than the plate folks do. And the roll beam market can be busy if there's a lot of building construction going on, where the plate market might be slow if John Deere's not making any tractors. So you have to consider that. If you have a project that may be particularly schedule sensitive and you know that you're going to bid it in March and you're going to want the first material on site in July or August, you need to kind of look into that. One may be more readily available than the other. One exception to the roll beam rule, if you will, is if there's a lot of curvature in your bridge, whether it be horizontal curvature or vertical curvature. Most states, I don't believe any state will allow you to cold curve or cold camber a roll beam. It all has to be done with heat. Heat curving a beam is as much art as it is science. And what oftentimes happens is when you first start to put the heat to a roll beam to try to curve it in whatever direction you want, that heat starts to release some of the residual stresses that were resulted from the rolling process. And that beam that started out straight is going to kind of stress relieve itself and go somewhere and bend in some direction. And you got a 50-50 chance it's not going to go the way you want it to go, which means now you have to put some heat into it just to get it back to straight, and you can start to straighten it or curve it in the shape you want it to. So bottom line is there's a fair number of man-hours involved in heat curving a roll beam. And again, it's as much art as it is science. So if you've got a lot of camber or curvature, especially curvature, it may actually be more economical for the fabricator to take a piece of plate and cut a banana shape out of it, which will be the flange, top and bottom, and just weld it up in that shape. He knows exactly what he's getting into. He knows what it's going to take him. He knows what it's going to cost. There's a little bit of material wasted when you cut that curved shape out of what started out as a rectangle, but that may be minimal compared to the time you might have spent otherwise trying to heat curve something. So an answer is, if you're not sure which way to go, show them both on the drawings. I'm not sure I heard anybody mention a consultant's name here. Was there any consultants in the room? There was one, okay. Obviously, you're going to have to convince your owner to let you take the time to design both and to show both. But the chances are that the amount of time it's going to take you to actually develop the plate girder alternate and show it on the drawing, that may be the easiest thing you do in a set of contract drawings. And this way it allows the contractor and the fabricator to make the most economical and fastest selection to suit the project right on bid day. And as the owners, you're going to get the full benefit of whatever that economy is. Whatever is going to be cheaper, he's going to have that in his bid, and he's going to put every penny of that savings in his bid because he wants to be low on bid day. If he comes back after the bid and says, hey, I'd like to change it from a roll beam to a plate girder and with the same thicknesses, web and flange and so on, and I'll give you this much money back or whatever, is he going to give you every penny he saves? I'm sure that he is, but maybe he won't. But so anyway, if you want to assure that you get all the savings, show it on the bid documents. For girder spacing, generally speaking, wider is more economical. If you can increase your girder spacing enough between girders such that you can eliminate a girder line, you're absolutely positively going to save money. You're going to have fewer girders, fewer linear feet of girder to be detailed and fabricated and so on down the line. Imagine you had maybe a two-lane bridge where you thought you were going to put in 5 girders at 9 feet on center so that you had 4 bays times 9, 36 feet. If you can increase your spacing from 9 feet to 12 feet and have 4 girders at 12 feet on center, so now you have 3 bays at 12 feet, 36 feet, you're going to eliminate 25% of the girder that needs to be fabricated. You're going to save a lot of time and a lot of money in the shop. You're going to have fewer bays, 1 less bay with cross frames and bearings and so on and so forth, more savings to go on. Now, it's possible, because that different girder at a wider spacing is carrying more load, it's possible it may weigh more. It's not likely. It's possible. Well, it's certainly going to have more pounds per linear foot of that member that you're designing. But remember, you've got 1 less girder altogether. It's possible you may have more pounds in the job, but probably not likely. Even if you do have more pounds of material in the job with the 1 less girder, you're going to have fewer dollars, for sure. So how wide is wide? If wide is good, how wide is wide? Up to 10 to 11 feet for spans up to 140 feet, which I guess is just about exactly the cutoff for short span. So ignore that second bullet. But we're suggesting go to that kind of span, and you'll probably, if going to one of those spacings allows you to drop out a girder line that you otherwise would have put in, look at it carefully and consider doing it. You'll save money. That considers all kinds of the fact that you have to form a different deck. You may pay more for the forming materials. Your deck might be a little bit thicker. There might be a little bit more reinforcing in it. But for the cost of steel, the wider girder spacing is going to save money. You're probably not going to significantly increase the cost of the deck such that you're going to negate the savings on the steel. So but you have to consider that. You have to give a little something back, but you get something for that thicker deck. The deck may very well last longer, especially if the thicker deck ends up in a little bit more cover over the top mat or rebar. That's going to protect that top mat, which is usually the first thing that goes. So you may have some savings there. You may get another benefit, which you might not have expected, in that once you have more dead load on each of the girders, and again, if you have fewer girders, you're going to have more dead load on each one. That's going to actually tend to dampen the vibration that girder might experience as traffic goes on and off of it. To date, we've tried to deal with human perceptible vibration in bridges by controlling the live load deflection. And we're learning that live load deflection is not necessarily related to the vibration that we might feel as we're sitting stopped on a bridge with the truck going on and off in the other direction. The building people know all about this. If you go to a big open shopping mall where there's a sidewalk kind of cantilevered off in front of the buildings on the second level, oftentimes as you're walking down that sidewalk, you can feel some vibration. They know how to solve that, and it has really nothing to do with the deflection limits. It has to do with the frequency and so on and so forth. And dead load is a good way to dampen the frequencies and get them out of the objectionable range. So long story short, you might get another benefit from the thicker deck that you hadn't even thought about. You also need to consider future redecking operations during your preliminary design. If you're wider girder spacings, you may find that when you go back and strip some deck off and try to move traffic around and restripe, you're probably going to want to make sure you have two girders under each lane of traffic under any given condition. So you might need to think about that a little bit, maybe make some notes on the drawings for if you've widened your girder spacing, that for future redecking, you might need to do this in order to accommodate a different lane configuration. So it's just something to look at. Some states have artificially narrow girder spacings just so that no matter where they put the traffic, they're going to have two girders under the lane. That's probably a false economy in the long run for the life of the bridge. But you need to consider that. Here's a good example to make the point about girder spacing and economy. This is a project in Pennsylvania. The bridge in the foreground, the bridge in the background was built in the early 70s. Traffic loads went up. We needed additional capacity. The bridge in the foreground was built in the year 2000. Now, everything about that bridge in the foreground is the same. It has the same spans, has the same structure depth. Everything about it is the same except for the fact that the bridge in the foreground has 4 girders. The bridge in the background has 6 girders. A picture is worth at least 600 or 700 words in this case. You can clearly see that the one in the foreground is going to cost less. Even if the flange may be a little thicker or the web may be a little bit thicker, there's going to be a whole lot less work involved in that bridge. Here's another example from Salt Lake City. This is a major project that was done on a design-build basis in order to increase traffic capacity for the Winter Olympics that were in Salt Lake 2000 or 2004, whenever they were there. They had a need to increase capacity quickly, and so it was done on a design-build basis. These are 15-foot deep girders on a 15-foot spacing. And I expect that if you leave it up to the contractor to decide what's the fastest, most economical way to go, he's probably going to find it. And in this case, the wider girder spacing did not scare him off at all. Thicknesses. How thick should it be? How thin should it be? If I'm doing a plate girder and I have to determine what those thicknesses are for the webs and the flanges, what should I be using? The recommendation is for stiffeners and connection plates, at least 7/16, probably a ½ inch is better. For plate girder webs, again, as shown, interestingly enough, the DOT responses to these two questions had a minimum of 3/8 of an inch. Well, 3/8 of an inch is really difficult to deal with in the fab shop and during construction. If you've got a 3/8 inch plate girder web, you're probably going to have a lot of stiffeners on it, which is just going to add cost in the shop. Real thin plates are difficult to weld. They want to shrink and move all over the place. When you make a plate girder with thin webs, it's hard to pick up and move. It's just not worth the little bit of material savings you might make between a 1/16 of an inch here and there to actually handle it and get it actually built. And you're probably going to be adding a lot of stiffness. For girder flanges, we're saying 3/4 inches. We didn't ask what a minimum width should be for a plate girder flange, but we tell people these days 12 inches. So your minimum girder flange would want to be 3/4 by 12. Again, anything less than that, when you try to pick that piece up in the shop, it may be 50, 60, 80 feet long. It's really just, it's very limber, very flexible, maybe a little hard to deal with if you violate these minimums. For plate availability, there are basically 4 plate producers in the United States. Showing the capacities stopping at 4 inches thick here because that's the limit in the AASHTO design spec. The first guys there, ArcelorMittal, go much greater than 4 inches thick, but we didn't bother to put it on the slide here, as do the folks at the end there, Claymont. You can see the thicknesses, you can see the widths. The first 3 listed there also have the high-performance steel available, the HPS 70W. In the case of Nucor, they can only provide the HPS up to 2 inches thick. And for the third one, obviously their HPS goes to 2 inches thick also. These are the folks where all the plate girders are coming from in the US. Plate size preferences. Again, if you're doing a plate girder, you want to kind of minimize the number of different thicknesses you have in the project. Fabricators are subjected to a minimum order thickness of for any given size. And if you have a lot of different thicknesses, their need is going to be less than the minimum, but they're going to have to order the minimum, so they're going to be having a lot of waste or having to figure out how to hold it and use it for another job somewhere else. So try to limit the number of thicknesses that you do use. For thickness increments, at least 1/8 of an inch difference on a job, up to 2 inches thick. If you've got material on there up to 2.5 inches thick. If you have material on your project over 2.5 inches thick, increase your increments to 1/4. So again, that's the increments on a given project. How many thicknesses should you have? Don't be changing a material size for a 1/16. Even though we showed you that mills can produce plate to very large widths, fabricators would prefer to bring it into their shop between 72 and 96 inches wide. It's easier to ship on a truck or a train that way. It's easier for them to handle in the shop. They can do it just a little quicker and easier. If, say, for instance, you had a deep through plate girder and you wanted to have a web that was 9 feet deep, well, then the fabricator is going to have to handle it. His preference might be 96, but if the job requires him to build something wider with wider plate, he's going to have to figure out how to do it. So don't be limited by that, but just know that. For wide flanges, there are basically 3 producers in the United States. The most commonly used for bridges would be Nucor. Nucor makes a bigger, deeper, greater selection of longer, deeper, wider bridges, girders that typically would be found in a bridge. The Nucor only recently went to 44 inches deep. I think they started availability of that sometime in the middle of last year. So they're not commonly used, but they are certainly available. About the longest you're going to get a roll beam from any one of these folks is 120 feet, and maybe a little less than that. In the real deeper shapes, in the heavier, deeper shapes, the maximum length is probably something less than that because it just gets to be too heavy when it gets long. For a lighter shape, it also might be something less than that, the maximum length, because it's difficult for them to handle in the mill to extrude a piece, if you will, that only weighs 30 pounds a foot, 100 feet long or something. So the heavier, deeper thickness, heavier, deeper girder beams have a little bit less maximum length, the ones you're likely to be using on a bridge. The spec for roll beams, most of these, well, all of these 3 producers will first be making their material to ASTM A992. That's the standard for a roll beam these days. That compares to ASTM A709 grade 50S in the A709 spec, which you're most likely commonly calling out for your bridge material. So those 2 are the same. The minimum yield is 50 KSI. There is no HPS for A992 or for A709 or for roll beams at all. I don't know if there's any plan to try to get to a 70 grade for the beams. I don't expect that there is. The HPS, by the way, is the newer material, recently developed. It's 5 or 6 or 7 years old now. It's a 70 grade material. It's commonly found in the plates, in plate girders, but again, you won't see it in the roll beams just yet. This spec has pretty much replaced the old A36, and it's also replaced the old A572 grade 50. Another issue that the document addresses is differential dead load deflections. How do you get differential dead load deflections? There's a couple of different ways during the construction that you might get that. And the question is, how do you handle it? What do you do with it? How do you take care of it? One thing that might lead to differential dead load deflections would be phased construction. If you either have an existing bridge and you're building a twin that you want to ultimately brace back to that, at some point in time, that new bridge is going to have certainly different dead load deflections than the existing bridge when it's just the steel is up. Another way you might do that, if you're just building a new bridge but in different phases, and you've got some of it up and the rest of it's coming along, once you get the deck on the first part, you've got all the dead load on, it deflects. Before you get the deck on the other part, the steel's still up in the air with the dead load camber in it. The way you would brace that steel that doesn't have all of its dead load on it back to the steel that does have all the dead load on it would be just with a top and bottom strut back to the full dead load portion. That will allow the other part to come down when the rest of its dead load comes on, and those two struts will come down and just sort of follow the new steel down as a parallelogram. You may remember an accident that happened in Denver, might be 4 or 5 years ago now, where they were widening a bridge. They had an existing bridge over an interstate, and they were going to widen it 1 or 2 lanes. And the construction worked out that the contractor put up the first new girder next to the existing bridge. And maybe it was Friday afternoon and the weather changed. They didn't really have any plan to what they were going to do to brace that girder by itself. So what they ultimately did was they just put a piece of angle from the top flange of the new girder back to the deck of the existing bridge. And they did 3 or 4 of these along the length of this girder, which might have been 80 or 90 feet long. Well, the weather stayed bad, and it was a while before they got back there. This bridge, by the way, was on a downhill grade. And what probably happened is, as that new girder kind of crept downhill a little bit over a 3 or 4 day period, that strut that was just attached to the top flange had to follow that beam down the hill. And as it rotated down the hill to follow the beam, it became a little shorter relative to the existing bridge, and it just pulled the new girder over, which swung down and ended up about 2 feet off the roadway below, and a couple of cars ran into it, and it just took the top off the car, and so on and so forth. If there had been a strut connecting the bottom flange of that new girder back to the bridge, well, the same thing would have happened, but the whole girder would have pulled over just a little bit instead of tipping just at the top. So the story is, or the lesson is, if you're going to put struts on something, put them top and bottom to keep whatever you're attaching to upright rather than tipping the top relative to the bottom. That was a long story before I got to the bullets. Omit the cross frames if you can between phases. That's one way to deal with differential deflection. Just ignore it. Otherwise, single angle struts. You also get differential dead load deflection with curved girders. The outside one is going to deflect differently than the inside ones. The science there and the analysis there is felt to be beyond the scope of the collaboration, in that the collaboration addresses standards and standardized issues, and every curved bridge is the same, and it was kind of difficult to try and put that all into a document that really wants to be standard. The third issue is skewed girders. How do you deal with differential deflection on skewed girders? And we do have some information on that. Let me show you what that's all about. Kind of a funny looking bridge, but it makes the point. First of all, the arrow on the skew angle of 45, the AASHTO spec requires that for any skew angles greater than 20 degrees, the cross frames be placed in at right angles to the girders. Below 20 degrees, your cross frames can either follow the skew or they can also be normal. Most people prefer to keep them following the skew at less than 20 degrees. Again, interestingly enough, several states responded that they let the cross frames follow the skew beyond 20 degrees. One state, I think, went up to 30 degrees. So even though the specs say it, the AASHTO specs say it, the states are free to do whatever they want. We also recommend that avoid putting a cross frame in sort of right close to the end of a girder like that, shown up in the top there. What's going to happen there is the top end of that cross frame is not going to deflect very much because it's right there next to the abutment. The bottom end of that cross frame will try and deflect a little bit because it's 6 or 8 feet or whatever off of the abutment. So that cross frame is going to have to try and accommodate that, which is either going to twist the frame or it's going to rotate the top girder and lift it up off its bearing or whatever. So the clue is, the advice is, try to avoid putting a cross frame in a situation on a skewed bridge where one end comes in right next to the end of the girder and the other one does not. Down at the University of Texas, they're doing a little research talking about lean-on bracing. Lean-on bracing would be where you don't have all the bracing in a bridge, all the bracing we're used to seeing, that you brace 1 or 2 bays, and then you put these struts in top and bottom to another girder such that the girder with just the struts on it sort of leans on the braced bay that's in the middle. In this case, what we would do is on this top place, would put just the top and bottom strut between girder 3 and 4, and maybe a full cross bracing in here, and maybe just a top and bottom strut here too. So that these two girders are well braced to one another and can't rotate relative to one another or each by itself. So that if this girder is connected here with just the top and bottom strut, it can't rotate either because it's connected to something that won't rotate. So that simplifies the bracing in the other bays, in the lean-on bays, if you will. We'll be seeing, I think, some design guidelines on that in the not-too-distant future from the University of Texas. They've got 1 or 2 bridges where they've actually constructed them and they've instrumented them to see that, confirm that they're working the way that the analysis says they should. Anyway, if we're trying to build that bridge, get that out of here. Here's what a cross-section would look like through the bridge. This is girder 1, which was the longer girder at the bottom of that last section. It has more dead load camber put into it because it's going to experience more dead load deflection because it's longer. The differential dead load deflection between each of these girders is 1.5 inches. So this one would be cambered 4.5 more inches than the one on the other end. So how are we going to put the bridge together? How are we going to put the cross frames in there? Well, again, starting from here, what the contractor does, he wants to hang that cross frame just pinning the top bolts on each girder. Then he pushes over the bottom of girder 2, puts that bolt in, pushes over the bottom of girder 1 and puts that bolt in. So the cross frame was fabricated to be square, and the girders are then twisted out of shape so that they can accommodate that square cross frame. It's actually very easy to twist these girders out of shape when they're up in the field, as long as the deck's not attached. If you were to go back and do some kind of torsional stiffness analysis of a long girder or a roll beam or whatever that's sitting on a pier 60 or 70 feet apart, it's pretty easy to go in and grab a hold of that girder and just twist the middle. And it doesn't have to twist a lot to be able to put these cross frames in. But so now we've got the cross frames in between girders 1 and 2. For girder 3 and 4, how are we going to get that one in? Well, first of all, we pin these 2 out. Then we tip the thing a little bit and we pin in the top of girder 3, and then again we push on the bottom of girder 3 and put that bolt in. We repeat that process between girders 3 and 4. So this is what it looks like when all the steel is up and no deck is on. So we've taken all the girders and knocked them out of plumb in order to get the cross frames on. This is when the contractor wants the steel erector wants to get paid and go home, because all the steel is up, he's ready to go, he's finished. Unfortunately, sometimes a job inspector will come in and say, well, that's not what it looks like on the drawings. It shows the girders plumb on the drawings. What are you going to do? Get that erector back here, or somebody fabricated something wrong. What's going to happen? Well, what happens is when you pour the concrete deck on, all the deflection comes out, and this thing just rolls down as a unit, and it ends up the way it's shown on the drawings, with all the webs plumb and ready to go, within tolerance, and there's certainly going to be a tolerance associated with all of this. But when you're back in that previous stage with the girders a little bit out of plumb, if you've got a long span and maybe a fairly shallow girder, it probably wasn't designed to accommodate the lateral component of the dead load that's going to get into that beam as a result of it being a little out of skew. So your consultant maybe needs to consider that. He probably didn't, because he didn't realize how they're going to be put together. But this is the way it's going to happen. We're seeing more and more of these bridges. All the straight right bridges, the easy bridges have been built. And the roadway guys won't let us, take the curves out and make the bridge straight. So we're dealing with more curved bridges, more skewed bridges. So we're seeing these issues come up into the field, and occasionally they're creating a problem. But this is how they're put together, and it needs to be considered during the design phase. Regarding bearings, the recommendation is use elastomeric bearings if you can. And today's elastomeric bearings can accommodate big loads, big rotations. They're very durable. Elastomeric bearings are the ones you most commonly find under big pre-stressed concrete girders. So if they're going to work under a pre-stressed concrete girder, they're sure as heck going to work under a steel girder. Unfortunately, we have a history of putting other kinds of steel bearings under steel girders, because that's what we've been doing for decades before we had elastomeric bearings. So we need to catch up with what's available currently on the market today. Use elastomeric if you can. They will be the most economical. And you can use pot bearings next. There are some design guides available that tell you how to design these things. One of them is another collaboration document shown here. There's still an older chapter from the Highway Structures Design Handbook out there that has some bearing information along with an Excel spreadsheet in it. To give you some relative idea on prices for bearings, now don't get excited about these numbers. If the dollar numbers are correct today, then they're going to be different tomorrow. If they're correct in New England, they're going to be wrong in Arizona. But just to give you a range of prices relatively from one type to the other, you can see that there's quite a bit of a difference between an elastomeric bearing at $225 and some kind of big gee-whiz spherical bearing at $1,200. Doesn't seem like much, but if you've got a bridge with a lot of bearings on it, you know, you start to save $1,000 at every point, and all of a sudden you've got some real money to talk about. So use the elastomeric bearings if you can. That's sort of the overview of the bridge layout, how you might design the bridge in general. Let's get a little bit of details on girder design here. We'll look at 3 or 4 different things. I better hurry up. If you're designing a plate girder, you're going to have you're going to try and change the amount of area, material area in the flange as your moment curve changes across the length of the girder. So when do you change the area? When do you make it bigger? When do you make it smaller? Well, the guidelines are no more than 2 shop splices in any field piece. A field piece is probably somewhere between 60 and 80 feet long. So that'd be 3 different pieces of material, 2 shop splices. Again, minimum, maximum changes in so much as how much you would change from one thickness to the next. But the most important thing is only change the thickness, the area in the material in the flange when it makes sense. When the material you're saving is worth more than the labor you're going to spend to actually make that butt weld. How do you know when that is? How do you know how much material you have to save? There's a chart in the document that gives you some instruction. Basically, you just look at the thicker material on the top axis and the thinner material on the bottom axis, find out where they intersect. You'll find a number there. You multiply that number times the width of the flange, and that tells you how many pounds you have to save to rationalize making the splice and cutting it and welding it and so on and so forth. In this case, if you were going from a 1.5-inch flange to a 1-inch flange, say it was 16 inches wide, you take the 70 times 16, I think that's 1,140 pounds. So you say, okay, how many feet would this thinner flange have to run before I saved 1,140 pounds at a 1/2 inch thick times 16 inches wide? And that tells you if you've got enough of that thinner piece to go, that if it's worth doing it. And there's some footnotes here and some that explain the gray area. But it's a pretty simple rule of thumb, and it tells you how much you have to change. Once you've decided to change the area, what do you change, the thickness or the width? We're saying keep the width constant. It's much easier to fabricate that way. Just change the thickness. And let me show you some graphics indicating how they do these things in the shop to explain why we're recommending you just change the thickness and not the width. Here's what it would look like in the shop if we were going to actually build a flange out of 3 pieces of plate and change the width. The plate in the middle is wider because that's going to be where the wider piece of the flange is. So we've got 3 pieces of material. We have to bevel these edges here, same thing on the other side in order to make a full pen weld later. We pick up 3 plates, lay it on a burning table, strip one each into 4 sections. We're going to end up making 4 flanges here. So I put 3 pieces on the table. I take 12 pieces off the table. I fit them all up. You can see they're starting to look like flanges now. Tack weld, 8 tack welds, put on 16 runoff tabs so I can start and stop my welds. Make that weld, which is going to be done probably with a guy just holding the stick in his hand because it's only 12 or 16 inches wide. Probably not worth setting up any kind of automated equipment to do that. Pick those up, turn them over, which doesn't sound like much, but this thing might be 60 feet long now, and it's got about as much stiffness as a piece of wet spaghetti. So it's probably going to take 2 guys and 2 cranes to pick it up and rotate it and put it down, times 4. You may actually spend a man-hour picking up and turning over these 4 pieces. Now we're going to go ahead and back gouge and weld and continue the process, knock off the runoff tabs, taper that thing down to make it look right, and now I'm finished doing it by changing the width. If, on the other hand, we're going to change the thickness, now I'm going to start with 3 pieces of plate that are the same width. The piece in the middle is thicker, so I'm going to have to taper it down to the thickness of the thinner piece before I put the bevel on, so there's an additional operation there. But now I just fit up these 3 pieces, just put on 4 runoff tabs, make 2 welds, maybe 72 or 96 inches long. Now it's worth it to come in and set up some magnetic tracks next to that purple line, which is where the weld's going to be. Get an automated weld going back and forth, however many passes it takes to fill that thing up. And at the risk of suggesting that the previous handheld welds are not good, which I'm not saying, chances are you're going to have fewer issues with this weld here instead of those other 8 welds, if only because there are fewer stops and starts. If a fabricator runs into any problem with a weld in the shop, 99% of the time it's where he started or stopped it. Well, I've got fewer starts and stops here. If only for that reason, this weld is likely to pass UT and RT first time every time, whereas the other one, you might have to go back and fix something or repair something where he started or stopped. So better chance, fewer problems, fewer welds. Pick up one piece, turn it over. Now, this one piece is bigger and heavier, which may eliminate a smaller shop from doing it this way. But that doesn't mean you shouldn't design it to accommodate this way anyway. If the smaller shop can't do it this way, well, he can still take these 3 pieces and strip them up a piece at a time and fit them together a piece at a time if that's all he has the capability for. Anyway, you can see where this is going. Back gouge weld, take off 4 runoff tabs, pick up one piece, burn it off into 4 flanges, and I'm done. 2 different ways of doing it. They both end up with the same flange. Well, they both end up with a flange that does the same purpose. However, the second method will save you about 35% of the labor. Now, each way had the same amount of material in it. This one saves a whole lot of labor. Which one's cheaper? That's pretty simple to say. This also helps make the point that when people ask, well, how much does fabricated steel cost? Does it cost 80 cents a pound? Does it cost $1 a pound? Does it cost $1.50 a pound? Well, here's a case where we had the same number of pounds, but just by the way the contractor had configured his flange, forcing a different fabrication method, he's increased the cost of the steel because he's added the labor material. The pounds are the same, but he's added dollars per pound to the whole process. So think about that when you're doing the design. If you must change the flange width, and sometimes you do, try to do so at a bolted field splice where it's not going to impact this whole fabrication process. And again, allow fabricators to eliminate a splice within a shipping piece. Show that on the document, on the bid drawings. Let the fabricator make that calculation. Is it cheaper for me to just run the thicker material to the end of that piece and save the whole welding process? A couple of states actually make that statement in their bid documents that a fabricator can do that without even asking permission. Here's another example where that same thinking might help save some money. Here's that same funny looking bridge we had earlier. You can see that if we just used the thicker piece in the middle, we're able to use this slabbing method to put the flanges together. Now the flange or the girder on the top has the thicker material probably running a little more than it needs to, so you're wasting some material there, but it certainly is saved by the labor that was saved along the way. Stiffness, boy, I got to go quickly. Bearing stiffeners, just put them in normal to the top and bottom flanges as opposed to trying to tip them a little bit so that when the girder rotates under its dead load rotation, they come back to plumb. Nobody's going to see it. Nobody's going to notice it. It's probably not going to have any effect on the design. Same thing for box girders. For bearing stiffeners, the code allows 2 ways to attach them to the bottom flange, either full pen weld or just mill to bear on the bottom flange. We're recommending mill to bear on the bottom flange. It's going to do more than do the job. No full pen weld. It's going to curl up the edges of the corners of that bottom flange. This talks a little bit about the fit up between the underside of the bottom flange and the top of the bearing. If you have put a full pen weld on that bearing stiffener, it's going to warp the bottom flange a little bit just from all the heat that goes in there. And you may say, well, gee, it doesn't sit properly on the bearing now. The only place where you need a good fit on the bearing is the sort of the cross shape that would be defined by the web and the 2 stiffeners sticking out. As long as that cross is sitting on the bearing, then you've met all the fit up you need on the top of the bearing. Just a picture for stiffeners again. The left one, mill to bear. If you had a cross frame framing into that bearing, into that connection, the bearing stiffener, which oftentimes you do, you'd probably want to put a little fillet well on the bottom to pick up the transverse load from the cross frame. Other stiffeners, connection and intermediate stiffeners, again, they should just be put in normal to the top flange. For the intermediate stiffeners, those that are not carrying a cross frame, having that attached to them, the spec allows them to just be clear from the tension flange, clear from the tension flange welded to the compression flange. We recommend you go ahead and make that stiffener such as a tight fit on the tension flange. Sounds like it's more work for the fabricator, but in reality they'll use that tight fit to control the flange tilt while they're welding everything together. Minimum spacing between stiffeners. I've seen far too many drawings that have stiffeners that are about 6 inches apart, and the beam is a W36 or it's a 5-foot deep plate girder, and the stiffener is 8 or 10 inches wide, so now somebody's trying to get in this little 6-inch crevice to try to get 10 inches deep and do a weld and inspect it and paint it. Make sure there's plenty of room between stiffeners for access. Again, connection stiffeners, those being ones that have a cross frame attached to them, need to be attached to both the top and the bottom flange. Welds to tension flanges are allowed as long as the stress range in that tension flange is low enough so that you can weld to it, and in many cases it is. Does Indiana require no welding to tension flanges at the DOT? Do you guys have any requirements along those lines? Nope. Okay, good. Well, and I'll just click right through here. This is what you might do if you were not allowed to weld to a tension flange. This costs a whole lot more than welding to a tension flange. Don't do that. Some general details regarding girder design. If you've got a cross frame, you're cross framing into a skewed girder, and you're following the skew so that the connection into the web of the beam would be at a skew. There's 2 different ways to do it. You can either put a little bent gusset plate, or you can put the stiffener in at a skew in the first place. The bent gusset plate, believe it or not, is preferred. That looks pretty innocuous here when it's just a small skew, but as you get to a larger skew, as shown on the right there, not easy to make that weld, getting that stiffener in there, not easy to get it painted, really hard for the inspector to inspect that filler weld into the flange, into the web rather. It's a real bother. This is actually a lot easier for them to do, just put a bent gusset plate on there. For a cross-frame connection design, for a deeper girder, we're suggesting you just make a simple X with the bottom strut down to when that angle gets to be about 30 degrees. So as the girder gets a little shallower, now you're into a roll beam, put in an inverted K with a top strut. And if you're just a simple little roll beam, maybe a 24 or W30, just put in a channel or just a bent plate. That's probably heavier than a cross frame might be, but boy, it sure is a whole lot easier to fabricate and construct. If you've got a haunch girder, how do you transition into the haunch away from the bearing area? Do I run the same bottom flange and just bend it? Or do I put in a welded butt splice there between the flat part and the haunch part? Depends on how thick it is, depends on how wide it is. Your best choice here is to contact a fabricator if you're trying to make that decision. They each have their benefits, they each have their downsides. For curve girders, again, allowed to heat curve or to cut curve. I'm going to just skip right through boxes here, I think, because I'm running way over. If you need to know anything about tub girders, you download a document from the NSBA website that has an awful lot of good design information about tub girders. If you need to galvanize bolts for whatever reason, we recommend mechanically galvanized. The finish is more consistent, they're more readily available, fewer tightening problems. If you're putting shop bolts in that are going to ultimately be painted, do you put them in black or galvanized? Again, we recognize mechanically galvanized. When they get out to the field and those bolts need to be painted, they're going to get some kind of brush-off blast. They're going to clean up nicely. If you would put in a black bolt and left it oily, which you'd want to do so it wouldn't corrode between when you put it in the shop and it ultimately gets painted in the field, when they come back to blast it, they're going to blast all the oil off the bolt and make an oily mess all around the connection area, which means the paint isn't going to want to stick so good. So again, if you're putting a bolt in the shop and it's going to stay in there and be painted later, use a mechanically galvanized one. Corrosion protection, our recommendation in order, uncoated weathering steel or a shop primer or all shop applied. These two, depending on the contractor and the fabricator, it may be preferable to put all the coats of paint on in the field if you're painting it, as long as the contractor understands that he needs to then handle it carefully while shipping and erecting. There doesn't seem to be any disagreement that 3 shop-applied coats have a much better chance of giving you a much better coating than 1 shop applied and 2 field applied, only because you have more control, better control conditions. But again, if you put all the coats on in the field, all of the paint coats, it does require a little more care on the contractor's part. For bolt fang surfaces, if you've got painted girders, well, you're probably going to be certain to use a Class B paint or primer at least. If so, use the Class B and use fewer bolts. Same thing with weathering steel. Blast the fang surface. That'll give you a Class B surface and allow you to use a higher slip rating, and you can use fewer bolts. This is not in the publication, but it's a question, again, that very commonly comes. How big can I ship? How long can I ship? The first bullet, these 3 items, that's sort of the no-brainer. If you limit your shipping pieces within that envelope, just about anybody can ship it. That's interstate stuff, not a problem. If you want to push the envelope, you can get down here. These kind of sizes work in places like Florida and Texas, where everything is flat and state lines don't come very often, so you don't have to change permitting requirements. But this kind of stuff has been done on the road. Again, the document is available both at our website, at NSBA's website, and also at the AASHTO bookstore website, because it is indeed an AASHTO document. Just believe me, it's easier to find here. It takes about 2 clicks to find it here. It takes free registration and many clicks to find it there, but it's there.